Welcome back, everybody. This is AP Chemistry, and we're in Unit 10, and still looking at Section 1 and 2 of the gas laws. But with this time, we're going to be taking a look at the story problems that are involved with those. So it's a little bit tricky once we see the problems themselves, being able to pick them apart, and that's the focus of this tutorial. So let's take a look at a couple different problems here together, and we'll see how to analyze those as we go. A particular balloon is designed by the manufacturer to be inflated to a volume of no more than 2.5 liters. Now, at this point, we don't really know if what we're going to be doing with the problem, but I know that this is going to be a volume, okay? The balloon is filled to 2 liters, or with 2 liters, and so the question is, maybe this is going to be one of those Boyle's laws where we see a volume 1 and a volume 2. Okay, we're going to be filling it at sea level, which is going to be 760 millimeters of mercury, and in looking at this, if we're going to be just using Boyle's law, we can keep it in millimeters of mercury. Whatever we start with, we end with, and that's no problem. It's the ideal gas law that we have to watch out for. So if we see it at the 760 and it rises to an altitude and the pressure is only 500, now all of a sudden I see that I have a P1 and I have a P2. Okay, so I know that I'm going to be looking for this, and I see that the temperature is going to be constant, and so I'm just looking at P1 V1 equals P2 V2. Now remember the trend, that as my pressure goes up, my volume goes down. Here my pressure is going down, and so my volume should be going up. The question is it going up to a certain point? And we want to know if it's going to be bursting, okay? So I just plug my values in here. We saw that we had 760 to begin with, and that's going to be in millimeters of mercury, and it's at 2 liters. And so the question is, at 500, what is my new volume going to be? Okay, so finding for this, my V2 ends up being 3.0 liters. Now go back to the problem. It's saying, will the balloon burst? And that's a question. Okay, so I would interpret this at the end as yes, it bursts because this is greater than 2.5 liters, okay? So I would go ahead and justify as to why, and that way, if this is a 2-point problem, you've addressed both, okay? Defended it with your numbers. Now, let's take a look at the next one, seeing a 12.2 liter sample having moles of oxygen, okay? And we're gonna be seeing that's gonna be one of our keys here, and I know that this is gonna be in moles. And so I see, first of all, here's a volume. Here's my moles. That's an N. And let's see, the pressure of 1 atmosphere. Okay, so that's a P. And a temperature of 25 degrees Celsius. If all of this was converted to ozone, and that's an O3, that's a different gas. And so we're going to be seeing at the same temperature. So this temperature is constant, this pressure is constant. We want to know the volume of the ozone. Now, be careful here because we are converting from oxygen into ozone, okay? And so if we do that, this is a 3:2 ratio. So I want you to be careful here because we do have moles of oxygen, but we need to see what that would be in ozone. Okay, so if I do that, I'll end up with, let's see, 0.50 moles of oxygen. And I need to convert my moles of oxygen into moles of ozone because that's what the question is regarding. So 3:2 ratio. And so I end up with 0.33 moles of ozone, okay? That's the end value I need to be working with. Now, I can do this one of two ways. Since my pressure and my temperature are going to be the same, I could go 12.2 liters of any gas, and I started at 0.5 moles, and that's going to be equal to V2 of 0.33 moles. My V2 in this case would end up being 8.1 liters. I can get away with that because the volume of the gas doesn't really matter, and we've got the two number of moles as we go. But if I was going to be taking a look and converting my ozone, most people would probably approach the Pivnert, okay? The pressure that we've got in there is going to be 1 atmosphere. My volume is what we're solving for. I found my 0.33 moles. That's a 0.08206. And my temperature at 25 degrees was 298 Kelvin. So my V value in this case once again ends up being 8.1 liters. Either way works. Just keep track of those values and make sure you convert to ozone first. Okay. Now let's take a look at things other than just the standard story problems. But we're taking a look at the volume of a mole of gas at standard conditions. And I want to remind you of a couple things along the way. There's a couple ways we can solve this, and this is a good reminder for something that we did way back when we were doing some stoichiometry problems. Okay, so we have STP conditions. Now we have to remember what the STP conditions stands for. STP stands for standard, temperature, and pressure. Okay, now what that means is 273 or 0 degrees Celsius, 273 Kelvin, and this would be 1 atmosphere, or that's going to be 101.3 kilopascals, or that's going to be 760 millimeters of mercury, okay, which is also known as a torr. So we just want to watch out for those things as we go, and let's plug some values in. Now, the reason we want to make sure we are under these conditions is this would help us to figure out where this, if we're going to be using ideal gas law, where this value for R came from, okay? So that's what the point to this problem is. If I have 1 atmosphere of pressure, for example, because that's standard, and I have 1.75 liters of something, and we wanted to know the moles of a gas. Okay, that's going to be my 0.08206, and my temperature is 273. If I solved for this, my N would be 0.078 moles. Okay, so that's just plugging values in to the ideal gas law. But if you remember way back when we were doing some basic stoichiometry problems, we could just see if we were at STP, we could do something a little bit different. We had 1.75 liters of something, and we would bring back the number of 22.4 liters per mole. If we're at STP, we can do this, and we'll get, once again, 0.078 moles. See, that's what the 0.08206 does, is if we're in the standard conditions, it takes these values, and it will basically take the place of the 22.4 to 1 mole ratio. So that's what we're achieving with this. Either way works. Because that's what the R value gives for us with that constant. Now, let's take a look at how we can use some of these things in a couple of ways. We could do STP in a couple of ways, but we see that we have calcium carbonate, so we need to know how many grams of this to produce a certain amount of carbon dioxide gas. Okay, so what we're going to be doing is we have to first of all take a look at calcium carbonate, and that's going to be producing carbon dioxide gas, and we'll get calcium oxide off of there. So we need to produce 3.2 liters, okay? So if we're at STP, we could simply go 3.2 liters of carbon dioxide gas. That's going to be 22.4 liters per mole, and that's of carbon dioxide. And then I could take a look at my balanced equation, okay? And so this is a 1-to-1-to-1 ratio here. So 1 mole of carbon dioxide is in fact 1 mole of calcium carbonate. Then I could say, and sorry, this is moles. So then 1 mole of calcium carbonate is 100 grams. Okay, and so if I do the math here, I'll end up with 14.3 grams of calcium carbonate. Now, that's if I'm going to be using my 22.4, okay? You can plug things into Pivnert and then convert. Let's do that, and we'll be forced to do that if we're not at STP. So let's take a look at how we do this using the Pivnert equation. Okay, so Pivnert is PV equals nRT. We just have to be careful. This is going to be an atmosphere, so that's okay, 0.7. And we need to know my 3.2 is my carbon dioxide. We need to solve for N. That would be moles of my carbon dioxide, though, okay? And so then I see 0.08206, and my temperature is in Kelvin, so I need to convert this, and so that would end up being 283 Kelvin. Okay, because it was in Celsius, we've got to do that. So if my moles of carbon dioxide was solved for, I would end up with 0.096 moles of carbon dioxide. And then I would go back and say, okay, 1 mole of carbon dioxide from my balanced equation was 1 mole of calcium carbonate. And then I would say 1 mole of calcium carbonate is 100 grams of calcium carbonate. Okay, and so I would end up with an answer there of 9.6 grams calcium carbonate. Okay, so that's all we need to be careful of with that, and make sure you're realizing when we use PivNert, that's only for gases, so we had to convert over to our solid. All right, now let's take a look at this next one where we have some methane gas and we have some oxygen. As soon as you see two different values, guys, we have a value of this and we see it's reacting with a certain amount of this. Well, what I'm seeing is I have methane plus my oxygen that's going to be producing carbon dioxide, that's a gas, and water. This is a complete combustion reaction, and if I was going to balance this up, I would need two oxygens and two waters. But notice something. I have 2.80 liters of this, and I have 35.0 liters of this. This is, by definition, we're taking a look at the volume here. I need to figure out that. So this is by definition going to be a limiting reagent problem. So my CH4, let's follow this guy first. And I had 1.64 is going to be where did I get that number? My 1.64 is my pressure. Sorry, that's a 1.65 there. And so that's a 1.65. Then I have a 2.80 liters, and that's going to give me my N value times 0.08206, and my temperature is 298. Okay, my N in this case would end up being 0.0189 moles of methane. Okay, now let's follow, and we could go with completion with this, but let's follow my oxygen for a moment as well. So I have 2.50 liters, and that's going to be 35 liters worth. And I'm going to make that equal to N times my 0.08206. And my temperature is a little bit different on this one, 304. And so my N is going to be 1.75 moles of oxygen. Now, it's a limiting reagent, so let's solve that for my carbon dioxide. And so in my balanced equation, I have 2 moles of oxygen for every 1 mole of carbon dioxide. Okay, now the same thing here. I have 1 mole of methane for every 1 mole of carbon dioxide. Okay, so this ends up being 0.0189 moles of carbon dioxide, and on this side I end up with 1.75 moles of carbon dioxide. No, I'm sorry, I get 0.875 moles of carbon dioxide. So this is my limiting reagent. I only produce 0.0189 moles of carbon dioxide. And so I can plug that in for my N value, because remember, they're ultimately wanting volume, okay? So I have 2.5 atmospheres at the end. I want to know my ending volume, and I have a 0.0189 that I determined through limiting reagents. 0.08206 as my constant, and 398 is my ending temperature. So my ending volume after all of this is 2.7 liters, and that is of my carbon dioxide. All right, so limiting reagent problem still works there, and then we can plug in and move forward with the ideal gas law. Okay, now we're going to be producing hydrogen gas, okay, by electrolyzing water. Now, the reason this problem is important or significant to us is when we hydrolyze water, that means that we're going to be taking some water and passing electricity through it. That's going to be splitting the water into hydrogen and oxygen. And so we typically collect that in a little test tube. Okay, and so what we're going to be doing is she's going to be collecting some hydrogen gas, but it's going to be bubbling up into this. So we're going to get hydrogen gas, but as it's bubbling up, we're still collecting over water. So inside we have water vapor. And so water vapor is going to be evaporating into the test tube as well. Whenever we collect over water, when we see that, they talk about a total pressure of 758, but that's 758 millimeters total. And it does tell me that the vapor pressure of water at 25 degrees, what that means is at 25 degrees, the water is evaporating and exerting a pressure inside the test tube as well of 23.76. So Dalton's law of partial pressure says you just add up the components. So 23.76 millimeters is just my water. Okay, if I subtract that off, I'll end up with my pressure of just the gas itself, and that ends up being 734.24 millimeters of mercury. That's the pressure of just my hydrogen, or what we call the dry gas. Okay, now from there, if I'm going to be using ideal gas law, I do have to convert my millimeters of mercury into atmospheres, and so that ends up being a conversion of 760 millimeters to 1 atmosphere. Okay, so if I do that, the pressure of my dry gas ends up being 0.965 atmospheres. Again, that's just my hydrogen in this. Okay, and so that's the point behind this problem, is showing you how we collect a gas over water and derive a just a pressure of that one. Now I see that I had 152 milliliters, but remember Pivnert, that needs to be in liters, doesn't it? So it's a 0.152 liters, and that will equal my N value, because I need to know the moles of hydrogen collected. So that's my N value. Then I can use 0.08206, and my temperature ended up being at 298 Kelvin. Okay, so my temperature, or sorry, my number of moles ends up being 0.006 moles of hydrogen. Certainly from there, if they ended up asking for grams, I could convert that to grams. Okay, so pretty straightforward with that. The trick behind this is just understanding, if we collect something over water, what to do with that information. All right, so we see that, whoops, I don't know why that's cutting out. Airbags are activated, and I see that when a severe impact causes a steel ball to compress a spring and electrically ignite a detonator cap. This causes sodium azide to decompose explosively according to the following reaction. And I'll write that equation on there. Ultimately, we need to know how much of this sodium nitride, with 3 nitrogens, otherwise known as sodium azide, must be reacted to inflate an airbag to 70.1 liters. Okay, so that's the problem, what we're looking for there, what mass must be there. And again, just a glitch in the program there, but we have an equation of 2 of the sodium azides, and that is my solid, and I need to know how much. Here's my sodium, and I have 3 nitrogen gases here. I need to get 70.1 liters. The question is, how many grams of this? Okay, so now we're back on track with everything, and we are at STP with this. We could go a couple different routes with it, but let's just go ahead and use Pivnert for it. I have at STP 1 atmosphere. I have 70.1 liters worth that I need to produce. This is going to be of my nitrogen gas, remember. So that's my number of moles of nitrogen. Ultimately, I need to get over here, but we'll get that in turn. So 0.08206, and my temperature at STP is 273. I could have used my 70 liters, 22.4 to 1 mole. I could have done that. Okay, so I do this route, I end up with 3.13 moles of nitrogen gas, and then I convert it over into my sodium azide. So in the balanced equation, I saw that I have 3 moles of nitrogen for every 2 moles of of the sodium azide. And then I can just say, since that's moles, 1 mole of my sodium azide, and that ends up being a formula mass of 65.02 grams of sodium azide. Okay, that will give me a value in the end of 135.7 grams of my sodium azide would be needed to produce that. Okay, so all you do is just kind of plug values in. Once again, it's a problem with that. If we're at STP, you certainly could have gone 22.4 liters to 1 mole, and then I would jump right into this problem of saying 3 moles to 2 moles, and then 1 mole to the 65.02. You would have gotten the same answer. Doesn't matter either way. Okay, so Cool. We're ready to move on to the next problem. Consider a reaction now between a liquid methyl alcohol, and it gives you a density. Now, at this point, remember, we've seen enough of this where we're given a density of something. Um, what they're trying to give us is the number of grams, aren't they? So I can immediately just look into this and say, okay, if I'm given 50 milliliters of something, 1 milliliter's worth is 0.850 grams. Okay, we just have seen that so many times that I can immediately convert that right to grams because that's what they're trying to give us. And that's going to be of your methyl alcohol, which is CH3OH. Okay, so I've got grams of this. Okay, and we're going to be reacting it with 22.8 liters of oxygen and a pressure of 2 atmospheres. The products are carbon dioxide and water, and we want to know the number of moles of something. Okay, so I've got in this reaction, I see that I've got a couple of things going on. I have my methyl alcohol, and it's going to be reacting with oxygen, and it's going to give me carbon dioxide and water. Okay, if I was going to be balancing up, this would be a 2 to 3 to 2 to 4 ratio. Okay, H4O, H2O. Sorry about that. But notice something that they've given me two different values. I've got 42.5 grams of this, and also I've got 22.8 liters of this. This is a limiting reagent problem. They want to know the number of moles of water formed. Okay, so let's go and keep these consistent. Let's take a look at my methyl alcohol first. I had 42.5 grams of my methyl alcohol, and let's convert that into moles. Okay, so that's 32.04 grams for 1 mole of CH3OH. Now I look at my balanced equation, and I saw I have 2 moles of that to 4 moles of my water. Okay, this is going to give me 2.66 moles of water. Okay, now let's analyze for my oxygen. Well, to do my oxygen, we're given a volume, we're given a temperature, we're given a pressure. Let's use PivNert. Okay, so if I'm using PivNert to figure out the number of moles of oxygen, I plug my values in. I have 2 atmospheres. I have 22.8 liters worth, and that's going to equal my N number of moles, 0.08206, and my temperature is 300 Kelvin there. So that gives me 1.85 moles of oxygen. Now let's go ahead and convert my moles of oxygen. There was 3 oxygens for every 4 waters. Okay, and so once again, this is a limiting reagent problem. I get 2.47 moles of water. And so I simply circle my smallest answer. This is my limiting reagent, and so this is my excess. Okay, so I have more of this than I need. I'm only going to get the 2.47 moles of water. Pretty straightforward, but do make sure you indicate which moles of water you get at the end. Okay, 2 more to go, and then we'll be done with this section. In a chemical reaction, we get calcium reacting with hydrogen bromide. Okay, how many grams of calcium are needed? Again, this is just going to be a regular stoichiometry problem. So let's go ahead and start with a balanced equation. I have calcium and I have hydrogen bromide or hydrobromic acid. And I'm going to get calcium bromide off of this because they're going to swap and this becomes a +2 charge. I get a CaBr2, and hydrogen when it's by itself is diatomic. Okay, so I'm going to need to know how many grams of calcium I'm going to get out of this. We need to produce 24.2 liters of hydrogen, 24.2 liters of hydrogen by water displacement. Now remember what that means. Water displacement means that I'm going to be subtracting off the water because I have in this I have water that's going in here. We have a test tube that the reaction is going in here. So inside we have a pressure of 738. Okay, so inside is going to be 738, but that's total. And so if I use my chart, and this would be provided in the problem, excuse me, or we'll look it up on our chart. If I look up at 17 degrees Celsius, I'll see that water has a pressure, an evaporating pressure of 14.5 millimeters of mercury. This is my water. Okay, and so what I'm going to be finding is the dry gas, 723.5 millimeters of mercury of the gas. Okay, that's going to be my hydrogen gas, and that's just the dry gas. Okay, so now I use that value for my pressure, but be careful, I can't use piv nert in millimeters of mercury. If I have 723, I just have to remember to convert it into atmospheres. So that's a ratio of one atmosphere to 760, and so my pressure ends up being 0.952 atmospheres of just my hydrogen. Okay, now I can do the math with it. So 0.952 atmospheres, and I have 24.2 liters that I need. Okay, and I'm going to solve for my moles of hydrogen. Okay, remember this is hydrogen here, 0.08206, and my temperature ends up being 17 degrees Celsius, so that ends up being 290 Kelvin. So my N value ends up being 0.972. Okay, that's moles of hydrogen. But the problem is asking about grams of calcium. So let's convert my moles of hydrogen. That's 1 mole of hydrogen for every, let's see, yep, we're all balanced here, for every 1 mole of calcium. And then I simply look and say 1 mole of calcium is 40.1 grams. And so I'll end up with 38.9 grams of calcium is going to be needed. Okay, watch out when you see water, something collected over water. That's your key that you've got to subtract off your water vapor pressure. All right, last problem for us. We're going to be reacting 2.3 grams of lithium chloride with bromine. So let's go ahead and take a look at what that would look like on a balanced equation. And so I have lithium bromide, LiBr, or I'm sorry, lithium chloride to start with, LiCl. Let me get rid of that. And let me start that one more time. And so I have lithium chloride. We're going to be reacting that with bromine, okay? Now be careful, bromine is diatomic, okay? So that's going to affect our balancing, isn't it? I'm going to produce now my lithium bromide, and I'm going to get chlorine, which is also diatomic, okay? So if I'm going to be balancing it from here, I have two bromines, and 2 lithium chlorides. Okay, so this says that I have 2.3 grams of this, and I need to know how many liters of this. Okay, calculate the volume of chlorine gas. We're at those conditions, and it is, in fact, once again, by water displacement. Okay, so with water displacement, remember we've got to subtract that off. Let's go ahead and do that. I had 768.2 millimeters of mercury total. And they're telling me that we're at 10 degrees Celsius. So if I just look that up on the charts, I'll see that I get 9.2 millimeters of mercury, and that's going to be of my water. And so what I'd end up with is 759.4 millimeters of mercury of chlorine, and that's just my dry gas. Okay, so that's I'm going to be using that value in here, but before I can plug values in, I have to convert this over into my chlorine in the first place. Okay, so that would be going 2.3 grams of lithium chloride. I'm going to go grams would be 42.5 grams of lithium chloride to 1 mole of lithium chloride. And then I take a look and I've got 2 of these for every 1 of these. So 2 moles of lithium chloride to 1 mole of chlorine gas. Okay, this is going to give me a 0.027 moles of chlorine. Now, remember, they're looking for liters, aren't they? So I've got my moles, okay? I've got my pressure. And I do need to convert this over from, if I'm going to use piv nert, I need to convert that over. So that's 760 millimeters of mercury to 1 atmosphere. Okay, so if I do that, I'll end up with 0.999 atmospheres. Okay, so now I've got my components of my pressure, I've got my moles, and I ultimately need my volume. Okay, here's my temperature that's provided. So I've got the components, let's plug it all in. My atmospheres is 0.999. I'm solving for volume, and that will be in liters, and that is in fact what they're looking for. I found my moles through doing stoichiometry, so that's going to be a 0.027 and 0.08206. And my temperature is 10 degrees, so that ends up being 283 Kelvin. And so my volume ends up being 0.628 liters. Okay, and so that's all I need to do. They ask for just volume. You can leave it in liters in here. Please do indicate that you know it's liters. Otherwise, you could put that as 628 milliliters if you wanted. But they don't really specify there. You should probably indicate which one we're going for. All right, so those are some problems and variations, how we pick apart different story problems, and I think you've got enough to do some independent work.